want to welcome everybody to episode 2 of Humanity in Deep Space, Space Tango's webinar series. Just as a quick way of background, Humanity in Deep Space basically emerged from a need among an interdisciplinary group of people about to have a conversation, really a planetary conversation, about how do we maintain our humanity, how do we maintain our humanness as we transition into deep space. As most of you know, we're really already a spacefaring civilization. We've had people in space since the 60s. People have been to the moon. We've had people living and working in space on space station for over a decade. And we also have robots on Mars, which are really just an extension of us as humans. And so this notion of spacefaring really isn't science fiction anymore. It's reality. And as we see the things accelerating and transition to Mars, there are going, we're probably closer now than we've ever been to actually putting humans into deep space. Now, whether that's 5 years from now or 10 years from now, or 20 years, nobody really knows. But that's really the genesis behind this webinar series, these conversations. Today, obviously, we're going to be talking about farming Mars. Before we go, I want to put up the slide and thank all of our sponsors. Those are the sponsors you can see on the page. Leave them up there for just a second. Just want to let you know that we very much appreciate their support, their vision. They're all cutting edge thinkers and really out of the box and make these kinds of efforts possible. Also, I want to say, I mentioned that we have over 450 people in attendance from a variety of countries. I talked about a planetary conversation from Argentina, Austria, Belgium, Singapore, Slovakia, Pakistan, Indonesia, India, Paris, China. So we have a broad representation today. We're really pleased with that because we really do want this to be an international conversation. So having said that, I'm going to stop and ask each of our speakers to briefly introduce themselves. You have your bios in front of you, but I'll ask each one to start. And so I'll start with Harsh.
Thanks, Chris. My name is Harsh Bais. I'm a professor here at the University of Delaware in the Department of Plant Soil Sciences. My lab has been working primarily on interaction of plant and beneficial microbes. So we basically look at the communication which goes on in between how plants actually recruit beneficial microbes below ground and what are the cause and consequences of this association in terms of plant benefits. We look into the traits that these microbes induce in plants as far as the yield and protection goes.
Okay. Also, next, Joe Chappelle.
Hi, everyone. I affectionately refer to myself as a test tube clinker. I'm an academic at the University of Kentucky. And behind me, you can see some pictures which really give you a sense of my engagement in this enterprise in interplanetary agriculture. So I've been engaged with the Space Tango group and had the privilege of putting a number of plants up on the International Space Station and bringing them down and looking at them. But I also want to end with just the philosophical statement about me and what is really driving me in this endeavor. And that is that I really have the sense that the ready access to food, fiber, and medicine has been a key determinant in mankind's success as well as failures to explore new frontiers in civilization. And I think that's exactly what we're talking about here today.
Thanks. Gary?
Yeah, I'm Gary Studi. I'm a horticulturist, a plant physiologist, and a space biologist. I am the president and founder of Synergy, a consulting company that specializes in controlled environment agriculture here on Earth and space agriculture as we began to explore past the planet. I have had 25 plus years of experience working at Kennedy Space Center, developing systems to grow plants in microgravity or on the space station, to Moon, to Mars, and excited at the possibilities of the technologies that we're developing to go to Mars and beyond to become a planetary, extraplanetary species. So I'm happy to be here.
Thanks, Gary. Just a quick note, we do expect Governor Beshear to join us at some point for a few minutes because of interest in ag tech and the interface between ag tech and space. So when that happens, we'll introduce him. Matthew.
Thanks, Chris. So yes, I'm Matthew Mickens. I'm the Chief Science Officer at Elevate Farms. And at Elevate, we pretty much are launching indoor vertical farms globally. And the mission pretty much is to address food security issues. Not only just those that have just arisen since the pandemic, but food security issues that have been present for a long time, whether it be E. coli outbreaks or just not readily accessible food. Whether it be in harsh environments or high latitude climates, we're trying to address those needs. And all of our technology and what we use is based on 30 years of controlled environment ag research. And so basically, as we find ways to explore how to grow food in space, we are actually improving how we grow food here on Earth.
Yeah, and Matthew, you might say you spent how many years at NASA?
So amazingly, I was an intern there 10 years ago. And then I did a postdoc there in 2015 for 3 years.
Okay.
And so, I have, a couple of years of controlled environment experience.
So Twyman Clemens, co-founder of Space Tango.
Yeah, thank you very much. So as Chris mentioned, I'm the co-founder and CEO of Space Tango. Chris got to go to space. I had to stay on Earth, as you can see from our backgrounds. But what Space Tango does is we focus on microgravity manufacturing. So that's taking and understanding processes that require zero gravity as a value add. I'm actually sitting in front of our ops station here at our in Lexington. We actually have a plant experiment running right now. So that's actually the test tubes with fixation in them, and then all kinds of telemetry. And then also behind me is a video we get from the space station. And actually, an astronaut is working on some hardware right behind me. That's a live shot. So happy to be part of this, and appreciate Chris inviting me to talk about how we kind of look at these things, which is really not necessarily the science, but actually how do you build the environments to grow plants in a space environment, wherever that might be.
Thanks. I'm going to hold off on Maria just a second. I see that Governor Beshear has just joined us. How are you?
Good. How are you, Chris?
Okay. Let me just say a few words. Governor, thank you so much for joining us. This session on farming Mars and interplanetary agriculture. We asked the governor to join us because we know he's a strong advocate of ag tech. He's pushed a lot of really interesting projects in Kentucky, very innovative, which I'm sure he'll talk about. He's also expressed an interest in the interface between ag tech and space. He's very familiar with Space Tango and things going on at Morehead State University and other places. And so it made perfect sense to have him join us. And we're really pleased to have him spend a few minutes with us and talk to us about some of his thoughts and ideas. I might add, I've known the governor for a while, so it's a pleasure introducing him. I haven't seen him for a while. He's our former attorney general. And so let me introduce Governor Andy Beshear.
Wow. Thank you, Chris. And what Chris is referencing is we've known each other almost all of my life, at least. So good afternoon, everybody. I'm so pleased to be joining you all today for this forward-thinking webinar on the intersection of agriculture and aerospace, two industries that already play outsized roles in Kentucky's economy. Just last month, NASA landed its latest rover, Perseverance, on Mars, in a technological feat that inspired us all and maybe helped us all feel like we've been out of our house a little bit more in this last year. But the precision, the delicacy that it required in an unforgiving environment on a foreign planet more than 150 miles away, that is truly breathtaking. It fires up our imagination about what's possible, and is a reminder of what we as Americans and as human beings are capable of doing when we work together to do great things, when we push out that which divides us and that which in this pandemic I hope we've realized isn't all that important, and focus on what is possible for the greater good of all of us. I know many of the people taking part in this webinar, you think about issues like space travel and colonizing other worlds more often and more seriously than most folks. Whether in one generation or in 10, humanity's push to visit and possibly set up a base on Mars will require the most advanced technology to get us there, but then to sustain us. Doing so will require great advances in agriculture, meaning we need groundbreaking innovations on practices that date back over 10,000 years. The exciting news is these innovations are happening right here and right now in Kentucky. We can also see that these innovations will in turn spark needed advancements in food production and sustainability here on Earth. In Kentucky, we are laser focused on building the economy of the future. Dealing with something like COVID-19 has been difficult, and the loss has been hard to process. But we know that the end is near. We know that we are going to defeat the pandemic this year, and we're going to sprint into a future. And that future for us is unbounded. A post-COVID economy is going to be different. It's going to be different everywhere. So why not Kentucky, and why not us? So we're working for a Kentucky economy that works for all of our people, where we are no longer chasing the jobs of the past, but embracing the jobs and the opportunities of the future. Just so happens that space, aerospace, and agritech are two major components of Kentucky's present economy, making us primed and in a position to be leaders in these areas well into the future. As we build a stronger, more resilient, and innovative economy for the future, companies like Space Tango, App Harvest, and Kentucky Fresh Harvest, and many others are poised to take us to new places and greater heights. Agritech companies in Kentucky are pushing the boundaries on the size, scope, and productivity of indoor controlled environmental agriculture. Think about App Harvest, one of our newest publicly traded company in Kentucky, and it's in Eastern Kentucky. We believe their facility is one of the 10 largest buildings in the world with one of the most sophisticated LED lighting systems we've ever seen. They had a meeting in Kentucky just last night, and I got to join them and meet Martha Stewart, which a guy like me never thought he'd be able to do in his lifetime. There's companies like EnviroFlight. I was just talking to the CEO before coming to talk to you, where the use of black fly larvae is so connected to what some would call waste streams from distilleries and others, creating a symbiotic relationship with so much that we have going on right now. At the same time, institutions like the Space Science Center at Morehead State University and companies like Space Tango aren't just developing, they are launching and proving the technology to make sustained life on Earth possible. These two industries, they're already finding common ground, so to speak, here in Kentucky. Chris and Wyman Clemens, I'm sure, will share some insights into the cutting edge research they facilitated on the International Space Station involving seeds and plants. And let me tell you, gentlemen, we are so proud of you that Kentucky has taken that role on the International Space Station. As we look towards a brighter and a potentially very different future, I hope you'll join me in applauding, supporting, and even working within these exciting and futuristic fields. I want everybody watching today to know that my administration is doing everything we can to foster this type of innovation. This is our chance, and this is our time as a state, as a country, and as a world. When we look at what is possible with precision and reopening our minds to different planets, we also look at our own, knowing that our sustainability, our resiliency is at a point where in so many areas we must take action. We are finding it being pushed economically as well. And we want to be a part of that movement here in Kentucky. There's a chance to build a better world through the pursuit of this science. How about a world where nobody ever goes hungry? Now, to do that, we're going to have to increase our food supply by more than 70% in the coming decades. But I believe we can do that. But if we're going to do it, let's take the compassion we've shown each other in this pandemic where everybody counts and nobody should be left behind. And let's make sure that absolutely everybody benefits from it. And for folks that haven't thought about Kentucky before, give us a look. I know post-COVID, places where the density is higher might not be as attractive as they used to be. We offer not just a great workforce and a great way of life. We offer an opportunity to transform communities. We look for purpose-driven entities and projects and companies that won't just change the world, they'll change the community that they're in. And we are really starting to see that. It gives me hope that a better world is in front of us, one where we are better to each other, but we're also creating those types of opportunities I've always dreamed about for my kids and my kids' kids. And I certainly want them to be right here in our state. Chris, thank you so much for all your work. Thank you for having me today. We are so excited about what's going on here in Kentucky, about all of our facilities in both aerospace and agri-tech, but we're ready to grow. We are ready to grow. We've already seen significant growth in agri-tech and aerospace. We just announced a number of new facilities, and so we're primed. We're ready to go. I'd say the sky's the limit, but you all have proven that is not true. That there is a much bigger and a much greater opportunity out there for all of us.
Governor, thank you so much for spending some time with us and for your support of entrepreneurial space and everything you've been doing. So thanks. I know you've got a lot of stuff to do. So thanks for your time.
Thank you all.
So that's great. And let me go just a quick note. We are going to be recording. This session is recorded. It will be recorded and made available on our YouTube page. Several people have asked that. So let me now turn to ask Maria to introduce herself.
Sure thing. I am an agricultural scientist, and welcome everybody. I actually am part of KSTC. Chris Kimmel is the founder of KSTC, and he actually hired me. I'm an agricultural scientist, but for the past 10 years at KSTC, I have been supporting the development of tech solutions for a multitude of disciplines and many on the interface of disciplines here in Kentucky at KSTC. So over to you, Chris. Don't forget about Lynn. She is on the phone.
I agree. And our last, we have Lynn Harper, who is in NASA Ames Research Park at NASA in Mountain View, California.
Thank you, Chris, and my apologies, everybody.
Yes,
I'm having technical difficulties. So I just wanted to say I'm Lynn Harper. I'm lead for integrative studies at the Space Portal at the NASA Ames Research Center. And prior to that, I had the privilege of leading the astrobiology effort where we took a look at life beyond the planet of origin. And when life leaves Earth, we take our ecologies with us and we create artificial ecologies. Before that, though, I was lead for the advanced life support effort at Ames, where we looked at using agriculture as a life support component, not just for food, but for oxygen production, CO2 removal, and cleaning of gray water to potable standards. So looking very forward to interacting with this group to see what's happened in the past 30 years that we can use for our future explorations beyond Earth.
Let me start things off by asking, we talk about farming Mars, and I know that brings a lot of stereotypic ideas to people's minds. But first of all, let me ask everybody what do we mean by that? When we talk about, quote, farming Mars, what do we mean by that? And what is the one or two big hurdles that you see in making that possible and successful? So having said that, let me start with Harsh.
Thanks, Chris. I think the biggest challenge that I foresee, I'm not an astrobiologist by any leap of imagination, but the work that we do and the basic physiology that we have learned over time, I think the biggest challenge I foresee is how plants are going to cope up with that high amount of carbon dioxide. CO2 growing up in Mars, at least, which has basically the Mars environment has 95% of CO2. And that's going to be the biggest challenge. The other issue that I foresee is how can we specifically select a particular type of plant species that you're going to grow there. Forgetting about, even if we kind of deal with the CO2 challenge, which basically gives us yield in a very, very short amount of time. So those aspects, just to kind of off the bat to begin with, are the two biggest challenge that I foresee.
So I've asked everybody to kind of frame what they think farming Mars is about and what do they see as one or two big hurdles. So let me go with Gary.
Yeah, thanks for the question. There are several challenges that come up. One is the increased amount of radiation. You're going to have higher levels of radiation than we have here on Earth on Mars, and outside you get outside the Van Allen belt. So maintaining some genetic stability and productivity. The physiological problems of maintaining high CO2, watering is a struggle under different gravity components, the different medias, movement of water under differential gravity. So the real challenge is being able to adapt to this unnatural environment of partial gravity, elevated CO2, high radiation, and changes in fluid dynamics that just occur related to changes in the gravity sector. There's a lot of challenges, but they're exciting areas to look at.
Matthew, what are your thoughts?
Yeah, ultimately, I think farming Mars means we need to actually, it begins here on Earth. It begins here and it transcends through the journey and of course to the destination. And I want to point out, there was a post that I saw when Gary posted the link for this on LinkedIn. Someone actually said, we need to change how we farm here in order to ensure we know what we're doing when we get there. And I thought that was kind of profound because what we can do here, the capability of using controlled environment ag research pretty much equips us for those extreme environments. And of course, my expertise is in lighting. And so one of the challenges, of course, immediately that's especially on the surface of Mars, is you got to realize the light intensity is only 40% of what we get here on Earth. And so that's pretty much equivalent to like the light amounts received in Canada in the wintertime, which is it's not a lot. And then that's not including the amount of dust in the atmosphere that could also impede on that. And so when we get there, there is no doubt we're going to need some kind of artificial electric lighting source to pretty much boost what's naturally not present in the environment. Or even on the lunar surface where there's continuous light for 2 weeks, but then also continuous dark for 2 weeks, you're going to need some kind of supplemental lighting. And so right now, technology such as light emitting diodes, LEDs, using those in a manner where we can actually control the growth of the plant is going to be a necessity. Absolutely.
Okay, thanks. Twyman?
Yeah, I think from the viewpoint that I have and we have, it's really creating the sustainable system around it to support a plant, whether it's the lighting, whether it's the gas exchange, obviously soil nutrients, and then of course the required moisture. And so we do a lot of our work in modules that are about the size of 2 tissue boxes. Obviously, anything that is, and that work has been with, people like Dr. Chappelle, who we've done some research on, that's really seeing the effects that microgravity have on plants, and a lot of the work that Gary has done. But as you start to think about industrial sized work, whether it's on a planet or on the way to a planet, you've got to, we really have to think about what that whole feedback loop looks like. There are habitats on orbit right now that are operating that are much smaller, that can make about the size of maybe 18 by 18 inches of a little garden, but something that is going to create anything that beyond maybe the almost, I don't want to say a pet, but almost like a house plant, on any type of long duration flight. Anything that's going to create anything of any nutritional value is going to require quite a bit of space and quite a bit of budgeting, whether it's gas, scrubbing, water, everything else like that. So that's where my head goes right away is what you do there.
So Twyman, we've seen another person in and out of the time. It's a frame behind you. I see. Is that a live shot of the ISS of the astronauts?
Yeah. So this is that's Kate Rubens, who's a NASA astronaut. She's working on a most likely I couldn't look on my quick look, just looking in the Zoom. It looks like she's working on a rack. She's got a headlamp on. Her and another astronaut are working to fixing some sort of rack system. Not quite sure what it is, but yes, that is a live video.
Yeah, that's very cool.
Yeah.
Lynn.
So I think one of the challenges that we're going to have in agriculture on the moon and Mars is that we can't prepare for it in microgravity, because you can't take microgravity or 0G and draw a straight line to 1G and say all of the plant responses are going to fit neatly on that line. So the first time we practice growing plants in a way that can inform life support and future food products will be on the planetary surface. We can do a lot of prep work, but basically we don't know how the plants are going to behave in 1/6G and 1/3G. We assume it's going to be better than microgravity. It should be a less challenging environment, but it's also possible the plants will exhibit unique features that we don't see on Earth, and that those may be positive or those may be negative. And so learning to work with those is going to require in situ studies. I think the other piece is that when I was chief of advanced life support, I didn't do it, but my team did. They had world record wheat yields, and this was before genetic engineering or genetic modification of plants. I do think that when we're starting to look at implementation of plants as life support components or food sources for other worlds, we need to take a look at what genetic modification may offer.
Okay. Maria, you have a question you want to pose to somebody at this point?
Yeah, Lynn, perfect segue. So Tiffany Vora in the prior webinar said, like, don't sweat it. Humans have 4 million years on Earth and we've survived it. But plants have billions of years on Earth. So they have far more information that we probably haven't tapped on. What traits do you think we should be looking at or into when we go into microgravity or Mars or the moon, like you said, Lynn?
So I think that's a great question, and I think it's central. I think plants are one of the most understudied life sciences topics in NASA. So I think that we have not informed this field as much as we will need to if we're going to be using them for life support components. But basically, I think the answer is the same in each case. I think we do whole genomic analysis. We correlate it with proteomics. We correlate it with metabolic studies of what new materials or new constituents are made, which are not. And we evaluate the overall health in each one of the different environments and compare them. So it would my colleagues and I have talked a lot about doing a Mars greenhouse, doing a lunar greenhouse as an automated system before people even arrive in order to do these characterizations and use some of the organisms as pioneers in each one of the cases so we can do the comparison.
Yeah. Joe, what are your thoughts on this question?
So I think Maria already prefaced this, but plants have been on planet Earth for about 2 billion years. It's a long time. They've already experienced a lot of transitions, a lot of conditions that are somewhat analogous to some of the conditions that are on these extraterrestrial planets. And so I think there is a big reservoir in plants already. They have learned the lessons, if you will, and it's going to be up to us to help to evoke those learnings from the past of those plants to help them grow and do the things that we like them to do. You know, produce food, produce fibers, produce medicines. Those are the key hailstones that we need them to do. I want to just go also to something that Twyman said that I think is real important, and that is that my vision for growing plants on these planets is it's kind of like these big hoop houses, and there's going to be lots of green material, high density green material in that. And the psychological value of that for the human spirit is just going to be tremendous. It is already, we all appreciate that. Who doesn't like to take a walk in a green space? It's just, there's something about that humanity that is important for us to really appreciate, that plants are going to provide in addition to sustenance for us.
Now, I want to ask, going back to that point, bouncing off that point, we have these, we see these pictures of plants growing in space. We see animations and images of people's vision of growing in space. Matthew's got a nice picture behind him of some of the plants that are growing in Elevate, the vertical farm that he works at. But I think one of the big challenges in space across the board is that you can't take much with you. And so what kind of when we talk about these kinds of things, I mean, what kind of infrastructure, I differentiate between what I call expeditions, which are, 15, 20 people going to Mars for 3 years and coming back, as terms of settlements, which are much larger. But even in terms of, even in terms of expeditions and, say 3 years, or what kind of infrastructure are we going to need that's going to enable us to do this? I mean, we can't just plant them and put a greenhouse over them. Yeah, Gary?
Yeah, that's a great question, Chris. And I want to kind of circle back that during the work that we initially did that NASA was funding on a large scale was a project called the Breadboard Project, which was to demonstrate the feasibility of keeping one person alive at a one person for 1 year using bioregenerative life supports on plants. And out of about a decades of work here in a very large closed chamber, there were, as Lynn had mentioned, world record field yields, 4 times world record field yields of wheat, world record potato yields in 2/3 of the time, exceeding all kind of models for production. And that came from not any new genetics, but where we came up with was providing new environments and unmasking that potential. And the LED lighting is providing the potential to look at that even further in ways we can only imagine at this point. And out of that work, we found with that 30-year-old technology, 5 meters squared per person would provide all of the water that you needed. About 20 meters of plant material would get all the oxygen and CO2 and atmospheric, and that would provide about half your calories. So the design that we're going to have to do are smaller plants with higher productivity, small volume, lots of food that you can eat, minimum processing, and be able to utilize, recycle, and reuse those resources that are used, the water, the atmosphere, and the inedible biomass that comes out. So recycling, sustainability are all critical issues to reduce that footprint. And the final thought is that because of the radiation in environments and solar storms, these greenhouses will probably be buried on the moon or Mars underneath to give protection with the regolith. So technologies for bringing light in from the sun to pipe it in, or electric sources for electric lights to produce those plants and maintain that environment that will allow the cohabitation of both plants and humans in an environment, I think are critical infrastructures.
Anybody else have a comment about that?
Yeah, I think the other one is power. So basically, we were able to get world record wheat yields by running the lights 24/7. And in order to support people over a long duration on the moon and Mars, power is going to be one of the limiters. The more we have, the more we can do. On Mars, though, the interesting thing is when you get to food production, if you get to food production with oxygen removal and CO2, you cross the line of when that makes sense to do it with a bioregenerative system rather than just a physical chemical system with stored food. You get there at about 2 years.
Yeah.
So when we go to Mars, it probably is a good idea to have a full greenhouse, not necessarily for full food production, but for a backup for life support, because your physical chemical systems for life support, when they break, they fail completely. Whereas a plant usually has a very graceful degradation mode. I mean, that may not occur in a solar storm, but in other conditions, you'll start seeing that the plants have a problem in time for you to recover. So from a safety perspective, I actually think that bioregenerative life support, including food growth, offers a safety advantage during expeditions to Mars as well.
I think the point that Gary made is also very critical. I think I would rather blame Matt Damon for making things too simplistic. I think we have to basically start by doing some kind of prospecting in terms of looking for plants which would actually do the job for us if we are indeed going to farm on Mars or lunar surface. In terms of looking for plants, as Gary pointed out, very, very importantly, that you are actually looking for plants which can actually which will have shorter life cycle, so to say, and a very high harvest index, a very high yield index. And that's what you're looking for. You're looking for smarter plants. None of the plants, in my opinion, none of the plants that we actually grow here right now on Earth as our main staples would do good over there. They would not. All your cereals are greedy plants. So you have to basically think about from the scratch board, going to that prospecting that initially all the hunters and gatherers did. So we are looking for a completely different horizon and looking for these systems which may work out, keeping in all the technology, all the physiology, all the biochemistry that we know about plants, and all the soil impediments that puts effects on plant growth. So I really like what Gary pointed out. That's going to be critical.
Joe?
So, Harsh, I just want to say that I think Lynn made the point earlier that that we just don't know what's going to be successful in these environments. These are new environments. And I would suggest that there is a big reservoir in our extant plants, the plants that we currently have here on Earth. And we're going to need to do the experiment. We're going to need to take a diversity of those plants and see who is an outperformer in those new environments that Lynn so eloquently described. You know, we just don't know about it. I have to say I'm very optimistic. I think 4 billion or 2 billion years of experience is going to win the day here. You know, plants have survived a lot of different harsh, critical environment, a lot of transition. So I think there's hope, and I realize it's hope, but because we don't have the wherewithal to really test this right now.
Matt, I want to ask you real quick. You talk a little bit about lighting, how important it is. Of course, that's even you talk about artificial lighting. Obviously, that's solar based. I mean, you're capturing it in some way. I mean, how difficult is that going to be? I mean, it's one thing to say yes is what we need to do, but how complicated is that going to be, both scientifically and again in terms of infrastructure?
For the lighting aspect, there are going to be some challenges in terms of harvesting, like Gary mentioned, solar light, and opportunities like if we establish a habitat on the lunar surface, there are tons, of course, you know, radiation and light intensity levels on the lunar surface, but there is a way where you can kind of pipe in fiber optic systems and harvest the visible components that plants actually use for photosynthesis. And I actually, during my time at KSC, at Kennedy Space Center, I had a small project called the Solar Window Project. And it basically involved using a fiber optic system and just pretty much transmitting solar light into a growth chamber. And there are a couple experiments that have been published and done on that as well. But also, I do want to say, from a lighting standpoint, again, I'll point back to LEDs. They can be used to manipulate the crop in ways that benefit our astronauts. So we know for the billions of years of experience that plants have on us, they have adapted to, of course, how the sunlight and the solar spectrum changes throughout the day. Plants respond to it. When you change, simply just by changing the color of the light, it is a cue for plants to say, for instance, they change their architecture, they get taller, or if it's an extreme condition, they may have to protect themselves. The plants produce these pigments or these, a lot of the red pigmented colors that plants produce as photoprotection. And so we can replicate that using LED lights. And essentially at Elevate Farms, we're actually doing that so that we could, in a way, increase the nutrient content of our leafy greens so that we can provide a secondary source of antioxidants that would definitely be a countermeasure for the radiation environment in space.
Okay. Twyman, I'll ask you something real quick. You've done, Space Tango has done a lot of experiments on station in a zero-G environment with plants. I mean, what kind of impressions and lessons have you learned from that work so far?
Yeah, sure. So from the technical standpoint, it's fluid flow, and Gary alluded to this a little bit in terms of watering plants. When you don't have gravity, surface tension is your predominant force, and so you need to ensure that you have a wicking path from your water, your liquid source to the plants themselves, and the seedlings particularly as you're beginning to germinate them. You just can't, obviously, like a dropper or something like that, just drop water onto it. And so you have to be cognizant of that. At the same point, you need to be also cognizant that you don't want to drown the plant with surface tension being predominant. If you put too much liquid in, it does not get to the root. You can basically envelop, whether it's the root or the leaf or others like that, and basically drown it, very similar to, this has happened a few times with astronauts when they get water in their EVA helmets and it can pool on their face or something like that. Something very equivalent can happen to the plants themselves. So you've really got to think about the wetting path. The other is making sure that you're getting gas exchange. So it's a little bit different with plants, and if I don't say this correctly, I believe any of the scientists on the group will say this wrong. One thing we really think about is heat buildup. Since you don't have convective heat flow, instead of heat rising, it kind of builds these bulbs. You might have a similar thing, obviously, with gas concentrations. You have a little bit more, obviously, diffusion, which is not as gravity dependent or not gravity dependent. But that's something you've got to think about, is a little bit of airflow. And then the last one is just watching temperature. If you're doing something in a confined environment, particularly depending on what your light or your lighting regime is, you can really kick up the temperature quite high when you're doing studies on plants and whatever scenario. You want to make sure that you don't get out of bounds on your temperature requirements. So I put it into the kind of liquid delivery, gas monitoring and movement, and then really put them into those categories.
We got a lot of questions. We had a number of questions that came in before we gave people an opportunity to ask things beforehand. And we got quite a few questions about the soil. what is the soil? What do we need to do to enhance the soil, the regolith on Mars? Is that going to be in order to grow plants? Is that direction where we're headed, or I've heard alternatives that soil isn't really what we need to be doing at all. It's going to be in the ponics area with all the different hydroponics, aquaponics, and things of that nature. That's going to be the primary source. What are your thoughts on that?
So, I mean, this is something we actually looked at, and a number of my colleagues have used lunar simulant to grow plants. They've used Mars simulant to grow plants. And I think just from our experience, and I would defer to people who are more actively working in it, but our experience back when we were looking at this in the 90s was that we're going to optimize probably with hydroponics for the most part, and that we may use the soils of the moon and Mars to extract nutrients over long term, but we're not going to just plant them in the dirt. So at least that was our position at that time. And if we're using it as a life support system, I probably still would not do that, because we want to be able to control to life support quality, and soil is a little random unless we so work it that it's really not the regolith anymore.
Yeah.
So I think that's one, but I also think, if Joe is optimistic about it, I'm optimistic about it. And I think that if I were to put a challenge out, I would say, I'd love to have tunable plants. I would like to have plants that can respond to different changes within the environment, and that if I were to manipulate those changes, we could get particular outputs that are important at the time in the planetary environment to help manage a more habitable atmosphere.
Yeah, Gary?
Yes, two things. First, from Lynn's statement of tunable plants, Matt can probably speak at great length of the ability of using light quality and specific wavelengths to create all kinds of forms and structure and composition, and that's really neat things. But going back to the soil, or what we call regolith on Mars, it's really toxic the way it is. There's some perchlorates, but if you put them in, they kill the plants. So in order to use that, that's going to have to be cleaned up. It's pretty easy, it turns out, but it takes water. So that's energy and processing and a resource. So cleaning up the regolith is going to have to get rid of those toxins at first. And then the remaining elements, as best we can tell, are pretty stable. They're hard to release the nutrients. But there's really interesting works on ways of using biological systems, either microbial systems or, working through things like vermiculture to utilize, regolith as part of a waste recycling system. So you start turning that into useful soil and releasing those nutrients. There's a lot of nutrients, but they're just hard to get to. So there's some neat technology that's got to be worked on.
One of the things I wanted to ask also is, we're not going to talk too much about the actual food piece of this. We're working on another webinar specifically on food, the variety of food, the types of food, the social, cultural history of food, the importance of food in humans in their survival and effectiveness. But I want to say something about it because I can't remember who referred, maybe it was Harsh, referred to, Matt Damon in The Martian. People can't live on one or two things for years at a time or for much longer. So one of the issues is finding plants or finding techniques, maybe some of it's aquaculture or whatever, that are doable, that will provide a base for a variety of things to eat. What are your thoughts on, there's been a lot of thoughts about that, but I want to just get your thinking on that. And again, you can't take a lot with you, so.
Are you asking everybody?
Oh,
Matt,
sorry,
go ahead. Go ahead, Matt. Go ahead. Matt?
You're talking about just how do we get?
Well, what about, yeah, I mean, how important is it going to be? Aren't we going to have to find kind of basically, I'll call it feedstock for lack of a better term, of things that can make a variety of foods? Because the one of the things that we've heard a lot from a previous webinar was that so we had Tiffany Vora did, for example, one of those Mars analog missions, and one of the things that she came away from that was just the incredible importance of food and how important it was, and how the negative impacts of not having varieties of food available to people in those kinds of and that was just for 6 weeks on the Earth. It's going into deep space is of course unparalleled. So just that kind of that thought.
Well, I'll keep in mind, seeds are light, and we can take a bunch of them. And so I do believe that leafy greens and herbs, which, are very diverse in terms of just the number of cultivars and different species we can have at our disposal. But we do need to have that diversity, just, even for the sake of the psychological aspect, of having, just more than one source of food. And so, I believe that.
I know the military, for example, has found that, when you can get into food monotony, just kind of things, it actually over time, the soldiers begin to eat less and it begins to affect their health. So, I agree. We get into some of those kinds of things. Other thoughts about that topic, Gary?
Yeah. I think that the primary carbohydrate sources that we use as humanity, which are, I think, probably corn and wheat and rice in different places of the world, maybe cassava and taro, provide our calories. And those have a great number of different ways that we can utilize them. They can be stored, they can be processed and put into myriad types of food to take care of that monotony. But to get those, phytochemicals, those antioxidants, we're going to have to either, identify crops like, that are easy to take with us. Leafy greens, you eat a lot of them. I certainly like the idea of that. But also there are things in, terms of synthetic biology or growing out, types of, meat or cell cultures of food that can impart that flavor and texture beyond the growing. Those will probably not help in the life support, but on the psychological diversity of the food, there's technology that can be moving forward and I think will be essential.
Yeah.
So, Chris, I think there's an interesting story in the background of this, and that is Scott Kelly with the zinnias. I don't remember who did the zinnia plant experiment, the flowers, but it wasn't doing well. And so Scott, he was on the ISS, and he was using his free time to nurse it back to health, which he did. So it was important. And it's not just food, it's also hyacinth to feed the soul. It's flowers, it's plants, it's texture, it's choices. I think is another piece of this puzzle.
Right. Yeah, Matt?
I was just going to add to Lynn's comment about Scott Kelly. I was actually at KSC during the zinnia experiment, and during my outreach presentations, I actually use a clip of that story where Scott Kelly had to pretty much abide by strict protocols during the time when the flowers started to suffer. There was actually a fungus attack, and he had to literally ask permission, like, should I water these or should I not water these? Should I turn the fan on? What should I do? And he pretty much says, well, if we're going to be going to Mars, I need to be able to make these decisions myself. And
Right.
So what happened was, that whole experiment gave Scott Kelly autonomy, and he pretty much made the judgment call for himself, because that's what they'll have to do, if they're millions of miles away from Earth. And so plants gave them that opportunity, to exercise that sort of self-autonomy.
So it sounds to me like somebody on these crews need to be farmers or need to be botanists that have a really deep understanding of food. Would you just correct? I mean, and how you produce it and how you grow it, because you're right. They need to be able to do that on the planet and in deep space.
Absolutely. There will need to be at least one member on the crew with some kind of life science background where they can, take care of what they're going to essentially eat or feed themselves with.
And Maria, you wanted to make a thought?
Yeah, I wanted to ask the panel if you had to pick a discipline or a topic that you wish agricultural scientists and future farmers on Earth or future farmers for Mars should focus on, what would that be?
Ooh, that's a good question. That's a really good question. I don't actually have an answer for it because I'm looking at it primarily from the perspective of using it as an overall life support system. So things that can be optimized for carbon dioxide removal, oxygen production, potable water cleanup. But when it comes to food source, I would say it's diversity. Because when you're looking at food as a psychological benefit, you're going to want to have choices so that you can change your day. But there's another piece to it too, which is that everyone assumes that when you go to Mars, you land on Mars, you stay on there for a period of time, you launch from the surface, you come back. Well, I've been involved in a lot of space flight launches. They don't always go off in time. And you miss your window, you're not on Mars for 6 months, you're on Mars for 3 more years. So what you would want is
excellent point.
That would allow you that resilience.
Yeah, and I think that's an excellent point, Lynn, and that's one of the things that I think is important when we talk about deep space and we talk about Mars and other places. These are really, really hard problems, and a lot of things can go wrong that we have to adapt to on that. So that's a really, really excellent point. Somebody asked about microbes, soil microbes expected to grow in that environment. Any comments on that? And helping to provide nutrients?
Sure. I mean, I would be perfectly happy to use microbes. Again, everything that I would look at for life support will deal in how repeatable and reliable it is, even more than optimizing for space or mass power volume. But I'd use microbes in a minute, algae, any of it.
Yeah. I had another good, interesting comment about reminding us that a large amount of serotonin is actually in the gut. And so that's again, when we talk about food, it's so many different aspects of that. I want to circle back. I'll start asking some of the more questions, but I'm going to circle back to this question of cellular agriculture. Gary tacked a little bit on that. What is that exactly? When we talk about cellular agriculture, synthetic biology, as it relates to this question, what are we talking about?
That's a really good question and a real fuzzy definition with no good answer. In my mind, it's using either tissue culture or cell culture to, create and grow plants or produce, meat or meat type products that are now able to be processed as food. So you're growing food in a test tube in order to provide that additional flavor and nutrient and nutraceutical components, not as a complete substitute for growing food in a life support system. But it is taking that basic physiology, that cell biology, and implementing that in a way that is useful. And I think that ties into the earlier question of disciplines. One I think that's really overlooked is ecology, of how we are getting these closed systems of biology of people, plants, and microbes in a closed system. And then the second is sociology, how these solutions that we come up with are going to be adapted by the crews as they become resilient. The ability to eat large amounts of cultured food, or which plants are culturally appropriate and which mixes to enable a society to thrive on the planet.
I was reading an article not too long ago. It was interesting. It talked about if you had 1,000 people on Mars, for example, in a settlement of some sort, looking at caloric intake and what it would need for on Mars for people, that the estimate it would take about 300 kilograms of food each day, or 6,600 pounds of food each day to support those 1,000 people. That's not a terribly, a lot of people, and that sounds like a pretty big challenge. So, are we going to be able to hit things we're talking about? Are we going to be able to reach scale on these things and go beyond just 25 or 50 people, whether it's cellular agriculture or hydroponics or other kinds of technologies? Or do we still need to develop? Is technology not there yet?
My
Joe?
Yeah, go ahead.
So go ahead, Joe.
My sense is what Lynn and Gary mentioned earlier is that, and I think even Matt, there's going to have to be the development and deployment of a totally different high density type of agriculture. And that means that the plants are going to have to grow a little bit quicker, a little bit be shorter, and have the same productivity as if they were to grow really big. And I think that technology is still in the development phase, but I think there are experiments in the past of NASA that say that there's potential there to do that. So
yeah, Matthew?
It's a density issue. But let me just remind everybody that people have thought about this synthetic biology of plants for a long time. And many people won't recall, well, some people may remember there was a famous picture of the sunbeam. And that's a plant that is a composition of a sunflower and a bean plant. And it was the notion was that we are going to have plants that are producing multiple types of products from it. Those were just, very fanciful ideas. But nonetheless, I think that's the potential.
Okay, Matthew?
Yeah, no, absolutely. I was just going to say in terms of the density and the concept of stacking, to reduce the horizontal footprint. Even though here at Elevate, we're doing it now, but the concept is actually not new. And I have to say this, because I think my mentor, Ray Wheeler, would probably kill me if I didn't mention this. 1988, the biomass production chamber. And Gary probably could talk about this in great detail. They were actually already developing and building grow systems that were stacked on top of each other. I think they grew wheat, radish, and maybe some lettuce. But from 1988 to the year 2000, the biomass production chamber was operating at the NASA Kennedy Space Center. And so that concept of vertically stacking, the density, making them, really vertically stacked, it's not new, and actually it came from space exploration, and so here we are using it now too.
Yeah, Harsh, you want to?
I think that the challenges with high density cropping system that we have here on Earth, if you think about either growing them in hydroponics or growing them in soil and here on Earth, the high density cultures usually basically survive in our agriculture cropping system is because we actually provide them with huge amount of nutrients. Because what you are negating in that condition is the competition that plants would have with each other under a high density environment. Mm-hmm. So if you're thinking about growing things on extraterrestrial space, such as Mars or on the lunar surface, the thing which is at the short end at this point of time would be nutrients, as we can't carry much, as you rightly said. So I think if you're thinking about high density crops, and again, this is something which is actually already in making, where in terms of you're already thinking about plants which won't grow that big and would complete faster life cycle with a very high harvest index. But you have to also keep in mind there's a huge amount of ecology that we are missing here. In terms of all these high density crops face huge amount of intra-plant competition or interplant competition, and by providing them huge amount of nutrients, you're basically negating them, and everyone is happy. The moment you take nutrients away, plants will turn aggressive against each other. So you have to keep that also in mind.
In other words, like people, right? When
Yeah.
food gets scarce, table
Yeah.
manners change.
Yeah, it's like
Okay.
seeing anybody in the room. If they're hungry, they're aggressive.
Yeah. So go ahead, Maria.
Yeah, follow on Harsh's comment, and to probably Matthew and Gary, we talk about harvest index in agriculture, but can we take something that we can eat the whole plant? Can we produce something in the lettuce roots and just that would be nutritious and would provide something different? We don't need to throw anything.
Thoughts on that?
So
Yeah,
can
go
I,
ahead.
can I ask for clarification here? Were you thinking something like that you could genetically engineer on the planetary surface?
Yes, a type of lettuce, just like Matthew pointed at, protectins, anthocyanins, anything else that we can produce in the root of the plant that would be nutritious for human sustenance.
Okay. I had a comment that came in from somebody who said they were working with a team that proposed using carnivorous plants to convert regolith into sustainable soil. Any thought? I just thought that was an interesting comment. Anybody have any thoughts about that? There's a link there, and I'll share it with you afterward. Apparently when it was done. You guys see a Harsh?
Carnivorous plants have kind of an interesting evolution if you think about it. You know, the reason why, you know, they started eating bugs is just because they were found in a soil environment with a very poor nitrogen content. And then that's the only way they kind of started picking on bugs, I guess. So I guess I haven't seen, but I could be wrong in terms of, you know, how many of them are staple or edible, I would say. But, you know, in terms of cleaning environment, I haven't seen those in literature, right? So maybe the link, if you share, would probably be more.
Okay.
Yeah, I guess.
Okay. Yeah. Let me also make a point that anybody that's listening in, obviously we're covering a lot of subjects, a lot more detail. If any of you have a suggestion of an additional webinar or other topics that we may want to get into at more detail in the future, these are going to be a regular series. You can go to humanityindeepspace.com and there's a comment section. You can just sign in and leave a comment, talk and just reference Farming Mars, and we'll be sure to take a look at that, because obviously we need to be digging much deeper into a lot of these issues. Also, as we kind of close up a little bit here, it sounds to me one of the purposes of this is there is a lot that can be gleaned from space research or research that's primarily geared towards space that can help us create a more sustainable Earth, a more sustainable agricultural system on Earth, and vice versa. I mean, there's things we've alluded to, several things that are actually going on terrestrially that could have great, potentially great benefits in space as well. I know, Matthew, I want to go back to you because you made a comment to me. You kind of referred to it here, but about how much of the work that's going on at Elevate Farms, some of that technology came from space research.
Yeah, absolutely. Like I mentioned, not only my contributions in terms of studying light spectrum and using, the color of light to change the nutrient profile and the size of the plant. But I also do acknowledge we have collaborations with the University of Guelph. Shout out to both of the mics there, both Dixon and Stasiak. And they've had years and decades of research in terms of even having hyperbaric chambers that will actually where studies have been done to figure out, well, will the plant survive in different pressure levels? Like if there's a catastrophic failure in pressure, will the plant survive? And they actually saw that there are some plants that will survive up to 30 minutes in very, very low pressures. And so we have collaborations with them and have been advised by, the research in the collegiate level. And so, yeah.
Yeah, I think that's very interesting because I think we've got a great opportunity to translate some of this, which is the whole idea behind this concept of interplanetary agriculture. We call it interplanetary because it involves the Earth as well as a planet. And how do we make those connections, and how do we create the knowledge that's being gleaned on both sides to create not only a more robust off-space, off-Earth environment for growing and nourishing people, but also using that to create a more sustainable agriculture on Earth. And it's been kind of a spin-off from Humanity in Deep Space, and that conversation is going to continue. And anybody that's interested in that conversation, please let us know. Anybody else have a final real quick thought or comment? We just have a couple of minutes left before we finish up here.
So,
yes, I'm going to get back to you on the we're going to finish on the competition if you're going to talk about that. But if you want to say something else, go ahead.
Yeah, this is something else. Goes back to the question you asked about 1,000 people. And I think it's important that when you get 1,000 people, the only way that works is if you have abundance. This is not matched person to person with no excess at the end of the day, which you might do in a sortie style mission. This is, you're going to need storage, you're going to need excess, you're going to need backups. So I think that needs to go into the thinking as well, which is you're going to need to be able to store food, because if you get anything that happens and affects many of the crops, you have a very serious problem. So that hasn't gone a lot into our thinking, but it probably should. And again, because we could miss the first flight out of Mars and be on the surface, we probably should think about it for the first flight to Mars.
A real quick question. Do we think, we talk about what we can take. I mean, what about the thought of actually developing prior to humans going there, supply ships that maybe have part of the infrastructure on them, so that when the humans get there, it's not a question of where they can't bring them, but there's actually some technology and equipment there that would help them create that before humans ever go. Is that something that sounds halfway reasonable?
So that's a great idea. This is the first time I've ever heard anybody propose it.
Yeah, and to jump in there, I've seen that in those architectures, whether it's SpaceX's plans or others. One, you're testing the landing technology before there's people in it, but two, you're doing some prep work of the site. Even getting away from plants here, but ISRO, in situ resource implement or use to typically because you need to make some fuel for the return flight. And you probably want to make sure you can make the fuel before you get there. So,
yeah, that's a good point. Yeah, Gary.
Yeah, and there have been certainly some thoughts and designs over the years of modular systems that could be deployed on a surface that would autonomously start up. So by the time a habitat crew showed up, some of that Martian CO2 could have been converted to oxygen.
Okay.
They're conceptual, but they're really, really neat ideas. And one thought I did want to put out, as much of the NASA technology, like LEDs, come from necessity of the unique environment to get to space, which is now enabling, vertical farming, indoor agriculture, the remote communication, miniaturization of sensors, is improving controls, not only at the high-tech agriculture, but in more rural, more sustainable systems where you have that control systems of providing that security and autonomy to populations for their food.
Okay. Thank you. And again, one of the things we want to talk about in future events, we didn't really get much into the whole issue of plants as also the basis for medicines, pharmaceuticals in space, which are critical, and materials and building materials. Before we close up, I'm going to put, I'm going to talk a second about the Deep Space Food Challenge. And so Lynn, we're going to put that slide up if you want to say a few words about that.
Yeah, I don't want to take up a lot of time, but this is an international audience, and obviously you're interested in food production. NASA has a centennial challenge that, in collaboration with Canada and the Methuselah Foundation, that is open internationally. And I just wanted to leave this up for a second so that you can take a screenshot if you would like to participate and further information.
Thanks. I want to go back to and show just a couple of slides from Elevate that Matthew shared with us. Let me thank everybody for their participating in this. Thank everybody for their time. Thank everybody for participated in watching. And thanks again to our sponsors. We appreciate their support. We appreciate their creative thinking and getting out there with us on something that's a very, very interesting topic. Thanks to Chris Baker with 22 Solutions, who's doing all the production work. Also, other people that were behind the scenes as well. CC Conway, Barbara Flexter, Rob Gabbard, and Arthur Rouse with does a lot of the production work as well. So thank you, everybody. Thank you for your time, and we'll see you next time. Thank you.
Thank you.
Thank you, everyone.
Thanks, Chris.
Thank you.